Hi everyone, I'm Nick Karpwitz from the Max Planck Institute of Quantum Optics in Germany, and today I want to talk about birefringence, at least the parts that we're going to need for nonlinear optics. So when I say that a material is birefringent, I mean that for a given propagation direction of a light wave, there are two possible values of the refractive index. This can cause fields with different polarizations to move at a different velocity or in a different direction after they enter the crystal. And I say crystal here because normally when you see birefringence, it's in a crystal. It can also show up in other media under stress, or if you apply an electric field to them, but most of the time we're going to be talking about crystals, especially when we're doing nonlinear optics. So what does this mean? A beam propagating in the z direction can have a different refractive index if the field is pointing in the x direction or if it's pointing in the y direction. In nonlinear optics, we mostly use this for phase matching. The problem I want to address is this. If I send a beam into a crystal, how do I know what values of refractive index will I get on the fast and slow axes? A useful concept for this is the refractive index ellipsoid. So this is the indicatrix. This is a 3D ellipsoid, and the length of the three axes is given by the refractive index in the three principal directions of the crystal. So nx, ny, and nz. Here's the equation defining its surface, and it's also handy to put it in a matrix form like this. So if we visualize our indicatrix, it looks like this. And the z-axis and z, the long one with the higher refractive index in this case, I've marked that with an orange stick. For 4 out of the 7 crystal classes, nx and ny are the same. So I'm going to start with that because it does simplify things, as you'll see. Now, to find the refractive index for our beam, we want to look at the intersection between this ellipsoid and the plane perpendicular to our beam propagation. I'll bring in that plane now with its surface normal marked with the yellow stick. And at the moment that the lines are parallel, the propagation direction, which I typically call z, and the crystal z-axis coincide. We'll light up the intersection and we'll see that it's an ellipse. And the two values of the refractive index are the axes of this ellipse. And the equation of this ellipse is just given by the 2x2 matrix in the upper left corner of the matrix. What we typically do to control the birefringence is to change the angle at which our light propagates in the crystal, usually by getting a crystal polished with the surface normal parallel to the direction that we want. This direction is given by two angles, theta and phi. Theta is the angle relative to the z-axis, the polar angle, and phi is the angle in the xy plane, the azimuthal angle. And now we're going to use a lot of sines and cosines of these angles. So for the equations later, I'm going to use these abbreviations here. And so now what we're going to do is we're going to rotate our plane to a new set of angles. So theta 45 degrees, phi 90 degrees. Theta is applied first with the beam direction rotating from the z-axis towards the x-axis. We can describe this with the rotation matrix acting on the input vector of the matrix expression. And phi is applied next with a different rotation matrix. These two rotations change our input vector into rotated coordinates where we'll apply the refractive index tensor. We can, of course, take these two matrices, combine them into one matrix, which I'll call the forward matrix. We then rotate back in the opposite order. And remember, order of rotation matters in 3D angles. So first we rotate phi back to 0, and then we'll rotate theta back to 0. The two corresponding matrices can be combined again into one matrix, which I'll call the backwards rotation matrix, and this operates on the result of our index tensor multiplying the forward rotation matrix. So we can combine now all of these matrices into one somewhat complicated matrix, but really we're just interested in the 2x2 matrix in the corner, which is defining our ellipse of intersection. And now we can notice some nice things that happen when we have a uniaxial crystal where and x equals ny. So first, these off-diagonal terms will be 0. The ellipse's axes are nicely aligned with our beam's x and y axes. And the terms along the diagonal are going to simplify quite a bit. So in the first element, we can use sine squared phi plus cosine squared phi equals 1. And this will fully remove the dependence on the angle phi, leaving this expression for the so-called extraordinary index, which is the one that does depend on theta, which is described by this formula here. And the last element simplifies even further using the same trig rule, and now it's just 1 over nx squared. It doesn't depend on any of the angles, and we call it the ordinary index. So now let's watch the evolution of the intersection ellipse from a point of view fixed to our beam axis. Note that the ellipse only expands along a single axis. This is our extraordinary axis. Also note that as we rotate phi, even though we're looking at a different direction inside of the crystal system, the shape of the ellipse is fixed. This confirms our matrix math. The phi dependence is gone. Our nonlinear optical tensors can depend on phi, though. So this is nice for us if we're doing nonlinear optics. We have a free parameter to independently optimize the nonlinearity without affecting the refractive index. So now, if we're using a biaxial crystal, where nx doesn't equal ny, the situation is more complicated. So let's have a look at how it changes things. First, as we rotate theta, the result is similar, but once phi starts to change, there will be two differences. The ellipse's shape will now change with phi, and it's going to rotate as well. So those off-diagonal elements are no longer 0. The matrix is still symmetric, however. And that means that we can define another rotation to diagonalize it. That is, we can rotate our beam around its z-axis such that its x and y directions match the axes of the ellipse. This requires 2 more rotation matrices, one at the beginning of the sequence and one at the end. The resulting matrix is a beast. You can find it in the Lightwave Explorer documentation if you really want to see it. For now, I'll just say that the angle delta that zeroes the off-diagonal elements is given by this expression here. With that in mind, we can write expressions for the 2 effective values of refractive index, which are these 2 equations, and together with the angle delta, we can define our refractive index ellipse. One last bit of complication before we finish. So 2 of the crystal classes, monoclinic and triclinic, have susceptibility tensors that have intrinsically off-diagonal elements. Usually within the transparent region where we work, they'll be symmetric. So what that means is that the indicatrix is still an ellipsoid, but it can be tilted relative to the crystal axes. And not only is it tilted, but these off-diagonal elements have dispersion to them as well. So the tilt of the indicatrix can depend on wavelength. So we can't really think of it as a fixed object in space. It's wavelength dependent for these types of crystals. Typically, what we'll do a lot of the time is we will apply another rotation to the crystal system. Like I do this in BIBO and Lightwave Explorer for a given reference wavelength. For most crystals, at least the ones that we use, this wavelength dependence is weak, but you have to keep this in mind if you want to do really precise calculations near the edges of the transparency window of one of these crystals. Let's look at a simple example in Lightwave Explorer. So I've set up a simulation here, which isn't doing anything in particular. I just took LBO crystal, which is biaxial, and I'm propagating through at the angle theta 45, phi 45, which doesn't really phase match anything, but it's more just to show some effects. I am going to send in the light through just on the x-axis of the crystals. So my polarization angle is 0. I'm sending in the light onto the x-axis. But even though there isn't much nonlinear optics going on inside, I'm still putting light onto the y-axis of the crystal, and this is just being caused by the rotation of the refractive index ellipse by this angle delta. So we have to correct for this. The way we can do this in Lightwave Explorer, you can either rotate your light by hand, manually. So first we can set up our input pulses, which will look like this. So this is the light that I want to send into the crystal. One thing that I could do is I could just rotate by some angle. If I wanted to rotate by a specific delta that I've already calculated. But otherwise, I would just want to use a helper function called rotate into biaxial. And this will do this calculation for me. It will calculate the angle delta associated with the crystal. The fact that I have 4 times the letter D here, I'm just telling it to use a default value for each of its input arguments. So the first one is the material. So you have the index of the material here, followed by theta and phi inside of the crystal. And then the last thing it has to know to calculate this angle is the frequency of the field. So now it's going to rotate on its own by a certain angle. And now I can run the simulation, just calling the default function there, which will just run the simulation, which is just put in the interface. And then the last step will be rotate from biaxial. Which will undo the rotation from the first function. So now if we run it, you can see there's still a little bit of light left on the y-axis, but it's reduced by some orders of magnitude. So from nanojoule down to femtojoule. The residual depolarization is just coming from the fact that this angle delta depends on frequency and it depends on k vector, and our Gaussian beam with a Gaussian pole shape has a spread in both, so you can't perfectly correct for this effect inside of a biaxial crystal, but you can strongly reduce it just by choosing the right orientation of your crystal. All right, so that's everything that I wanted to cover in this video. Just remember, calculating the effective refractive index is just a matter of smushing together rotation matrices until you get something diagonal in the end. And you can visualize this process as finding the 2 axes of the ellipse at the intersection of the indicatrix with the plane orthogonal to our beam and figuring out its orientation. I hope this helps, and take care.